Hello, and welcome to the walkthrough of part one for uh, lab lab 5. This is the 64-bit ALU. I'll be walking you through the basic functions and how we build from 1-bit to 8-bit to 64-bit. One moment. Let me pull up these schematics. So this is our 1-bit ALU. You can see the opcodes up here. Pardon, let me uh, zoom in. There we go. We have all requested operations, as you can see. We take in 4 inputs, A, B, C in, and our operation, and output a result and a carry based on our needed results. Um, it's worth noting that we have a setup here to see if we have a sum or a carryout for a sum or a difference of two numbers, and we have our input going to carryout for A in case we have shift. All other outputs go through the result. The 8-bit takes these results and either compares them all, and if they're all equal, outputs a 1 for our cout. That is our comparison unit. And if we're not using a comparison, we just have a regular carryout. Um, all other results are put out in the resultant vector right here. Um, this is also fairly straightforward. Um, we have our two vectors, our carry in and our operation. For our first carry-in, we either use or we use a carry-in if we're not using a shift. And if we are using shift, we do not use that carry-in. For our 64-bit ALU, we have it all wired in series again. We also have a mask for our matching bits, so it works like it does in the drop FIFO in case we need that. Other than that, it is wired up completely like the um, matching system in the 8-bit ALU. We just incorporate that mask function, and the results are concatenated from each 8-bit ALU into a final output. Here you can see our simulation with different types of operations. I will change these to decimals so you can see what these look like. Oh, why don't I run this the wrong way? Should still be changing. There we go. My apologies. Some of the numbers are quite long, so they can't be represented by unsigned decimal. Um, so this does show the uh, all functions working as intended. You're welcome to check yourself, but for now, let's move on to part two. Thank you very much.
So for part two, our register file, we have two read addresses that we can index to read the outputs from one of these 4 registers, and it's just a 2-bit decode basically. So we'll select one of the 4 registers to read out from R0 or R1. And on the other side, we can write, and we use decode 2B to write with these 2 bits, 00 being the first one, 01 being the second, and 10, so on. And this is our write enable, so we will only write if it's enabled and the decode is selecting that register. And this is the data that we are writing to the register if we are writing. That's pretty much it. You can also replace this whole thing with a lock or IP core generated RAM so that it doesn't use as much space on the FPGA, and we'll probably incorporate that for a future lab.
Hello, I'm here to explain the data processing pipeline for Lab 5. The pipeline itself is actually fairly simple as it is mostly made up of IP core generated components with only uh, a few registers in between, as well as this program counter and our made register file. We covered the register file in part 2, so I'll be sparing that here. Our CB8CE is just something that counts from 0 to 15 in binary. We use that to parse through the instructions in our instruction memory right here. We then pass the data from that instruction memory on through this register from the informal IF stage to the ID stage, or the instruction decode stage. We decode it through a register file and split it up throughout our stage registers to make sure they propagate through the circuit as they should. For instance, we have our write enable for our register file that loops around into write back into our register file when we need to write through memory. Again, that's just one example. Um, and for the sake of brevity, I will leave the pipeline on screen for a moment just so you can take in where each signal goes, and I'll go through each stage and just explain what each signal is. So for our register file, we have a write enable, a write address, 2 read addresses, our data in, and our 2 data outs, 64 bits wide. For our stage register, we have a 1-bit write enable for our memory, a 1-bit write enable for our registers, and 2 pieces of data that can go through from our register file. We also have a write register that lets us know where to write into our register once we get that data from the memory. We propagate that through the execution stage directly into other stage registers, only to come out on the memory stage and split them where they need to. For instance, we use the 8 least significant bits to access the addresses in our memory data, or in our data memory. We use our write enable that we get in our ID stage, and our address that we get, or our data that we get from our register file in order to access or write memory, or data from the data memory block. We then here pass our write register, our write data, and our write enable back into the register file if we need to. That is our pipeline data process. Thank you very much for listening.
Okay, now we move on to part 4. So what we have is we modify our project.xml file. So we, in the user data path, we change the IDS to the pipeline. So, and what we do is we modify the pipeline.xml and we adding the registers. So we naming the register D memory data lower 32-bit and a high 32-bit. And also we have a register D memory address, and we have the register for I memory address, and register iMemory data, which is iMemory out. So in the next, we modify our pipeline.v. This is our wrapper verilog, because what we did is we draw a schematic design of our pipeline data path, and we generate to be a verilog file, and to let NetFPGA to understand, we need to read a wrapper file. Then we have the wrapper file, and then we set the register interfaces and also the input reset and clock. And then we put our parts to the wires with its input and output ports. So now we have the generic registers for our pipeline registers. Shows up over here, and then we also have the software registered and the hardware registered. So now we gonna go through our pipeline registers. So we have all commands. So we can write instruction, read instruction, and write data. Also, we can read from register and write to the registers. So right now I have my NetFPGA access. So I'm gonna CD to my team 7 and my lab 5. Right here we have our NF2 top bar.bit file we generated already. And we also have our pipeline register, which is the Perl files we made. So what we're gonna do is we first check Q all OKDs. So there's no progress of the OKDs. Okay, yes, next we're going to do the NF download to NF2 .bit file. After that, okay, it is done. After that, we need to do the RKD to run the daemon of our file. Then what we do is we do chmod to make the Perl file executable. Should be a plus X to our pipeline register. Okay, now let's try to read all registers. So you can see all zeros over here. So next we're gonna to write data. So where to write? We need to write 0 and the lower 30-bit to be 4 and a higher 32-bit to be 0. So now we have our data writing to address 0. So now we check all registers, we can see the data's over here. So okay, after that we need to check our instructions. So what we did is we pipeline register, and then we need to write. First, like let's do read instruction 0. It should be all zeros. Okay, now what we do is we write instructions. Write to instruction address 0 to be 6000000. Okay, 8-bit. Now we have our address. The instructions on address 0 be 6. Now let me read the instruction 0. Let's write to instruction 1 be 7 000 000. Now we read instruction 1. It should be 7 over here. Yes. So here is our demo. Thank you for watching.